let's say recall a spanning tree of a connected graph is a subgraph of G that is a tree, of course, and uses all vertices of G. Okay, so we use this term, it spans G. The vertex set of the spanning tree spans G. And in general, a spanning subgraph is just a subgraph that uses every single vertex of your graph there. Maybe not every edge necessarily, okay? So that's what a spanning tree is. Maybe it's good to draw a picture of one as well. So for example, I think this is literally what I drew last time. Let's change over colors real quick. There's many different spanning trees of this. One might be take this edge, this edge, this edge, and this edge. Right, red is clearly a tree, and every single vertex appears in the thing there. We could also draw like in blue. I mean, they're gonna have some overlap, but you could go blue edge, I don't know, blue edge, something like that. Right. The blue one's another spanning tree, a little bit different. There are other spanning subgraphs. If you include the 4 cycle or the 3 cycle here in a spanning subgraph, it won't be a tree, right? And if you have a spanning subgraph that's not connected, it won't be a tree, but these are ones here, okay? So a common question that we ask is finding a spanning subgraph, a spanning tree, especially of an underlying graph, is like in applications a useful procedure, because what you're looking for is like, imagine you have like a computer network of some sort or something like that, and a spanning subgraph is like a minimal way to like make connections between all the computers or all the things on your network without using every single road or something like that. So this was actually a classic question. This is how spanning trees sort of were first used. They were actually for wiring electrical networks in like the 30s or something like that in the Czech Republic. And one of the algorithms I'll tell us today for actually doing this was invented by, 90 years ago, basically, to solve this type of problems. And the algorithms are really, really simple. They're all greedy, and they're all like, just do the obvious thing, and they work. What we'll prove is that they actually produce what we want. So first I have to introduce another definition here. And this will be useful elsewhere in the class, but why not? Let's change. So if we have a graph G, we're gonna have a function that assigns weights to each of the edges of the graph. Like we're gonna call it a weight function. So I'll say an edge weighting of G, of a graph G, is a function from the edge set of G. So you map the edges of G to, say, the real numbers. You can map them to other things too. You can map them to any set you like, but it's most practical just to map to the real numbers here. And in practice, we won't even use real numbers. I mean, all the real numbers will just almost virtually always just work with integers here, but it's not going to make any difference here. I mean, that's literally the definition of an edge weighting. I'll just say that assigns weights to each edge of G, okay? But I mean, this second line here is literally just saying what the function is. By the way, I don't know if I have an easy like erase function here. I'm a little afraid to do this. Eraser. Yeah, okay. I want to name the weight function W instead of F. All right, so all it is, maybe we can look at our picture here. Like, here's a weight function where I say that edge has weight 3, 2, 7, negative 100, pi, I don't know, square root 2 or something like that. Okay, so I've just assigned a number to each of the edges of the graph. That's an edge weighting. There are also vertex weightings where you assign weights to the vertices. It's pretty natural, these notions here. But in applications and things like this, these are very natural, because suppose you're working with a graph here that represents like this is root 2, represents like some transport port network, like airports, right? Say these points represent airports and the edges represent direct flights between airports. Well, there's a way, there's a cost associated with edges in flights like that. The cost might be time, it might be money or something like that. So if you're looking to travel around, you may not always want to take a direct flight. It may be cheaper to go via somewhere else. And so like, it's not simply enough to know, oh, there is a flight there, but you want to know the cost of the flight in some capacity. So again, in applications, in practical ways, when we think about graphs of existing real world phenomena, it's very common that there's sort of a weight hiding in the background there. Okay. Another one might be like, a social network or something. There might be like a strength of friendship or something like that. Like I actually don't know of a social network that does that, but I mean, it's pretty easy to imagine such a thing. Okay, so what we're going to want to find is what's called the minimum weight spanning tree. And that's all that is that I've got a graph, I've got an edge weighting of the graph, and that graph, say it's connected, it has spanning trees, right? We've seen above here, we saw a red and a blue spanning tree. In general, you can have lots of different spanning trees, but they have different weights, right? I'll define this, but what's the weight of a spanning tree or of a subgraph? It's just the sum of the values on the associated edges, right? So let's say that here real quick. So given, well, actually, let's do a definition that's even a little bit more general than what's in the book. So given G and an edge weighting W, the weight of a subgraph H it's simply the following sum. So I'm going to define it like this. I haven't written this in the notes, but this is a very typical piece of notation as well. So the weight of the subgraph, we're defining this, right? Here the weight is just on edges here, but the weight of subgraph is, well, not really surprising. We sum up the weights of the edges who are in the edge set of the subgraph we're looking at, okay? So the weight of any particular subgraph is just the sum of the values of the weights on the edges of that subgraph. So the weight of G itself would just be the sum of all the edge weights that were assigned to edges there. But using this, we can talk about a minimum weight spanning tree. So a minimum weight, we usually don't use the word weight here, we just say minimum spanning tree, is a spanning tree. Well, again, this definition is evident here, but whose weight is minimal among all spanning trees of G. We should be working so minimum spanning tree of G. Okay, I don't claim this is unique. Not only do you have multiple spanning trees, you might have multiples with the minimum here. Let me draw a couple pictures here. These resemble the ones in the notes, but they're updated a little bit just to maybe make them a little more illustrative. Again, I know this concept's pretty easy, but so let's say we've got this graph here. So this is G, and then it has weighting 3, 4, -1, 9, 6, 6, and 2. And I'm not going to prove that this is a minimum weight one, although it's not hard to just sit down and check. But the minimum weight spanning tree looks as follows. One of them is take that edge, this edge, and say this edge. Okay. Red is spanning. Every single vertex is touched. It's also a tree. Actually, it's a very nice path. And if you compare it against all the other ones, if you just do it by brute force, you'll see that this one has minimum weight among those that exist. Let me draw the picture again, just to be crystal clear here. 6, 2, 6, 9, 4, 3, -1. Does anybody see another minimum weight spanning tree? In this case, it's relatively easy to identify another one.
Yeah, you just take the other 6 edge.
Yeah, precisely. In this case, we can just swap the two 6 edges here. So I draw this one in blue, right? So we just replace this 6 edge with this 6 edge. This is actually an important sort of like little key that'll come up here later. So this is another path. It's a different spanning tree. It has the same weight as the other one. So assuming the first one was minimal, this one would have to be minimal as well. Let me just give one more that's a spanning tree but not minimal, right? Just to confirm that it's not. So most likely if we take the 9 edge, you know, probably that's going to be bad. I don't know what I wrote in my notes here, but let's just say we take this one here, 6 and 3. Yeah. So, okay, I didn't write it down, but like, you know, what's the weight of these ones? This one's, what's this, 10? And it was 10, and this one comes out to be more than 10, right? I don't know what it is. We can add it up. Right, we had the 9 and we have a 2 and we don't have the -1, so we already have 11 from these 2 edges here. So this one, I'll put like a versus here, right? These 2 are minimal, but this one's not. Okay. So, okay, so first of all, minimum spanning trees definitely exist, right? There's only, if it were connected, there's only a finite number of spanning trees. Each of them has a weight, which can be computed, assuming that your weight function is finite, but we go to the real number, so it is. So you compute the weight of each of those, and then some of them have whatever the minimum is, and those are the minimum spanning trees. And so the goal of like today is, how do we find one of these? Like, what's an algorithm to do that? This one, I didn't even tell how I found it. Brute force works reasonably well here, but there are fast algorithms to do these things. We shouldn't have to brute force it at all, okay? And so let me give the first algorithm here. And then, so the algorithms are simple. The main interesting part here will be proving that the algorithms actually produced what they claim to produce, okay? Okay, so let's just call this, so the first algorithm here is Kruskal's algorithm. And let's say, so, okay, let's say the input here. I'm just gonna write this as a paragraph, like a simple statement here. So let G be a connected graph with an edge weighting W, right? Okay, and W goes from the edges. Here, let me just write it. Edge weighting W from the edge set of G to the real numbers, okay? We should assume it's connected, although you can run Kruskal's algorithm on a graph that's not connected, and you'll see what happens. It just won't produce a spanning tree because there aren't any. And then it's not clear what you're finding there, although you can make some ideas here. Okay, so what am I gonna do? I'm gonna order the the edges of G by their weight. Okay, so smallest to largest. Okay, so I just arrange the edges in order of the graph G according to their weight. There may be multiple edges of the same weight. Just break ties arbitrarily. It doesn't matter. Okay. And then what I'm going to do here is I'm going to go through this list. So begin with T is empty. So T is the graph that we're going to produce here. And how do I say that? Yeah, okay, so just begin with T empty. No reason to be really concise here. And now I'm going to pass through edges of G in order. So in the order that they were given here based on their weight. And add them to T if they don't create a cycle. Okay, and then we stop once we've gone through the whole list of edges. Right, every edge gets checked, and once an edge is checked, we either add it to T if we can, or we just jump to the next edge. Okay, so let me actually run this algorithm on the graph that we had here. It's very, very simple, but what were these? -1, 3, 2, 6, 6, 4, 9. I think that was it. So let's run the algorithm. Here, you don't even have to like order the edges, really, like write them down. Let's just look. So the algorithm says, we start with T is empty, so I don't have a graph yet. And then I'm gonna go through the edges one by one, starting with the lowest and going to the next lowest, and adding it to T if it doesn't create a cycle in T, right? So the first step is, well, -1's clearly the first edge. Adding 1 to my, like, you know, pending tree here cannot possibly create a cycle, so we add it there. And now we look here. Does adding edge 2 create a cycle? No. 2 edges aren't going to create a cycle in the first place here. So we add 2. Now the next edge to add is 3, and that can be added, doesn't create a cycle. And now finally we get something interesting. Edge 4, this edge of weight 4 should be added to the graph here. But we can't because that creates a cycle there. So we don't. Right? And then the next step is to add edge of weight 6. That was the next lowest. And now Kruskal's algorithm is it just depends on the ordering we picked. It's arbitrary. We either pick this one or pick this one. The algorithm doesn't care. And we'll notice from the examples we saw above, both of these are fine, right? It's 2 different outputs from the potentially. It just depends on like the coin flip, but it picks one or the other. And we know, fortunately, either of these would be fine. You know, suppose maybe just to update the graph to make it even more a little bit interesting here, let's add like this edge here that's of weight, I don't know, 11 or something like this. Then, like, you don't have to end in a step where there's this 2 options, right? There might just, like, this could happen in the middle of it, that you have to make this branching process here, okay? So the next step here would add, like, 9 can't be added because it creates a cycle, so we add 11, okay? Yes. Yes, yeah. And if we made the reverse decision, maybe just to look at it for a second here and chose this 6 instead of this 6, we still couldn't add 9 because it would create this cycle here instead of this cycle here. 9 was not going to be able to be added, whichever one we made. And then we add 11, okay? But actually, that should maybe give you pause for a second and say, well, wait a minute, what if I came up with like enough copies of each other that like somehow we yielded 2 graphs that weren't both giving the same value at the end, right? I mean, all that's asking is, does this algorithm actually produce a minimum spanning tree? So I have to prove that to you. I mean, it looks good, but it's so simple. It's not enough to just say this algorithm, you know, worked on this example, right? We know better than that. So let's actually prove that the algorithm's correct and produces a minimum spanning tree no matter what, okay? All right, so let's say, I'm gonna call this a theorem, but the theorem is just that Kruskal's algorithm is correct. Okay, so what did I write here for the statement? Yeah, okay, so let's just say the graph T produced by Kruskal's algorithm is a minimum spanning tree of G. So the algorithm's correct. It produces what we claim that it does, okay? All right, so let's do this in a couple of steps. So the first step is just, so one is want to show that T is a tree. Like, does the thing that we produced, is it actually, no, you know what, actually, we want to show, let's see here. Yeah, that it's a tree. Okay. What do we have to do to show something's a tree? What was the first definition of tree? Can someone tell me that real quick?
It's a connected graph with a unique path between every, or maybe connected graph without cycles. Is that what we did first? Yeah,
exactly. Let's use that definition. Although any of those definitions from the equivalence list could be useful to us here. But let's use note that it's connected and has no cycle for this case. So connected and no cycle. Which of these 2 is immediate?
No cycle.
Yeah, no cycle, right? Like literally built into the, into the algorithm is don't produce a cycle. So we don't have a cycle. Great. So the question is T connected, right? So is T actually connected? And that takes a second here. Actually, whether or not it's connected, well, okay, I'll state that in a second here. So is it connected? Let's see what happens if it's not. Okay, so suppose not. Suppose not. And let me draw a picture here. So if it's not connected, then it means there is, let's say capital Q. There's a component Q that is connected, right? It might literally be just a single edge. It's just take a component, like one piece of it. If it's disconnected, you have a piece, and then you have the rest. I'll call this V of G minus Q. This might be multiple components. This might not be connected, okay? Now, if there are no edges between these 2 blobs here, then what can you tell me about the original graph? If
there's no spanning tree.
Okay, so careful, like, oh yeah, okay, that's fine. Yeah, then there's no spanning tree, or in other words, the G is not connected at all, right? If like literally, if this cannot get joined over to here, then Q is a component of the original graph. In other words, the original graph is not connected. But we assume G was connected, right? I told you the input to Kruskal's is that it's connected. So if no edge, then G is not connected, which is a contradiction, right? So there are edges across this divide here. Okay, there's some edges. I don't know what they look like. Okay. Now I claim that the algorithm should have added one of these edges to the graph. Okay. So at some point when we pass through the algorithm, I'm going to see these edges here. Can adding one of these cross edges create a cycle? What does a cycle look like if adding one of these edges creates a cycle? Like, why can't I add this edge here, this one? Only if putting it in would create a cycle, meaning that I had a cycle that used some edges that I already embedded into my graph. And so the cycle would have to look something like this, right? This edge goes across between these two things. There's no cycle that uses this edge that lives inside of here or lives inside of here, right? It's got to cross the divide here. But if it did that, then this edge that crosses here was a part of my spanning tree. But I just said there was no edge across here in my T. I didn't claim T as a spanning tree. I'm just claiming that like this edge would have been present if I can't add this edge. It means that there's an edge present here. But that's a contradiction to the setup, the picture I made here. Q was a component. This edge should be part of that component there, okay? So so let's call this E. We can't add E, then maybe it's easy to say there's no edge across, then there's no edge here at all, then no edge at all. And then we have the same situation here, then G is not connected, okay? So there, like if you have a component here, there's always edges incident to it that can be added to your T there. Otherwise your graph wasn't connected in the first place, okay? Oops, I didn't mean to do that. All right. Okay, so that tells us that it's connected. That also means that it will be spanning, right? Because if it's not spanning, we'll have like some part that's a tree and then some leftover vertices. But the same exact argument is, look, you've got a big tree and a few leftover vertices. Like, why couldn't I add those to the thing? There need to be edges from what I've got so far to the leftovers. Otherwise, the full graph isn't connected in the first place. So there's some edges going out of my component. Why didn't I add them to T when I got to them? I should have been able to. They wouldn't have created a cycle. Okay. All right. So this means that T is in fact, spanning tree of G. Great. So it's of the type that we want, but is it minimal, right? So is it minimal? Well, that's what we have to prove now. So now we want to show, and this is the more interesting part of the proof, T is a minimum spanning tree. So it's minimal among spanning trees. We know it's a spanning tree. Okay. So first, let's let T star be a minimum spanning tree. Okay. So let's pause here for a second. T star is potentially some other tree. It's not the one produced by the algorithm. It's a hypothetical construct here. Does this exist though? Is it fair to talk about a minimum spanning tree?
Yeah, it must exist. But can we also say, like, it could have been produced by the algorithm if we ordered our vertices differently, right?
Yes.
That was arbitrary?
Yeah. So yeah, that's right, Van. So I mean, but that actually requires a proof. We don't know. Like, we know that the algorithm will produce a spanning tree, but we don't know that it can produce any desired spanning tree because the T that it produces depends both on the order, but also literally on the edge weights themselves, right? Now, what you've stated is actually true. Yeah, I see the thumbs up. You can get the spanning tree that you desire if you're careful. But yeah, we don't know that T equals T star. If we knew that, we're done with the proof, right? But we definitely know that minimum spanning trees exist because A, spanning trees exist, and B, there's finitely many of them. So just check them all. There might be a bunch of them, but just let T star be one of them. In fact, I'm not just going to let it be one of them. I'm going to let it be the following. So moreover, let T star be a minimum spanning tree with most number of edges in common with T. Okay. So maybe I can illustrate this. It's not the easiest thing to do here, but So here's G, right? And then the algorithm produced T, and T looks like something. We know it's a spanning tree. We don't know anything really about its weights yet, that it's minimal, okay? And then we also know that there are multiple spanning trees that are minimal. Maybe not multiple, we know they exist. Among all those minimal ones, choose the one that has as much in common with the red graph as possible, right? Like again, there's only finitely many minimum spanning trees. Choose one of the ones that's the best. In other words, that it matches up the most. So maybe it matches up like here and here and here and here, but otherwise is like different. Okay, they still hit the same vertices, right? They're both spanning, so that's why it's kind of like hard to draw. But let's just like pretend here. I don't know, something like that. Maybe I'll erase this one here, since that's not really a thing. Okay, so blue is T star. That's a minimum spanning tree, which exists, but we haven't found. We don't know what it looks like, but we know it exists. And red is T. That's the spanning tree that was produced by the algorithm. And these two have the most edges in common as possible. What I'm going to show here is that T and T star have to be equal to each other. And then that would prove that T is a minimum spanning tree because it's identical to a minimum spanning tree that exists. And the way that I'll do that is show that if there's an edge that's different between the two of them, I can alter T star somehow to get a new minimum spanning tree that's even closer to T. And that's a contradiction. Or if you want a procedure, you can run the procedure multiple times until you literally transform this minimum spanning tree into a new minimum spanning tree that's identical to T, which proves that T is also a minimum spanning tree. Okay, all right. So we've added that. So what do we want to do with that? So so the first step, yeah, is like if T equals T star, then we're done, right? Like if we got really lucky and literally hit this T star, which again, we know exists, although the algorithm doesn't produce it, then we're done. So assume that T is not equal to T star, okay? So if two trees are not equal to each other, it means there's at least one edge in T that's not in T star and vice versa, right? That's how we know that they differ. They use all the vertices, so there's got to be some difference in edges between the two of them, okay? So then let's let E be the first edge selected by Kruskal's algorithm that is not in T star, okay? So remember, they have to differ. So there's some point when I'm building up the red graph here that I choose an edge that's not one of the blue edges, right? As the algorithm runs, what's the first time that they're different? It might be the first edge, right? Maybe the first edge in building the red one is different from something in the blue, but maybe they correspond to each other for the first 20 steps, and the 21st step, I get a red edge that doesn't appear in the blue one, okay? So, but E is the first one. Why do we care that it's first? It has to do with the weight. Like remember, the edges of edges of T are ordered somehow by weight. So like that'll be a helpful notion there, okay? So now I want to make the following like really nice observations here. Let's consider T star plus the edge E. Remember, this edge E was not in T star. What happens when I add it to T star? So T star is a...
You get a cycle?
You get a cycle, exactly. This has a cycle. And actually, it's important for us now. Not only do you get a cycle, how many cycles do you get?
Just one.
You actually only get one. I'll leave you to think about that a little bit. Certainly, if you draw examples, you'll see when you draw one edge to an existing tree, you'll only get exactly one cycle, not multiple. It follows from the tree properties that we proved the first time, but I'll leave that for you guys to think about, okay? So it has I'm even gonna say unique cycle C, right? This graph here, like if I add one of the red edges that wasn't in the blue graph to the blue graph, I'm gonna get a cycle C. So let me even draw that here. In fact, since we're using colors here, we can even like do something really nice here. So what does that look like? Oh no, I think backwards. It looks almost all blue, except for the red edge that we just added to that graph. And this is E, okay? So T star plus E has a cycle, and that's the cycle there, okay? Now, we know though, but T has no cycle, right? T is the other one, the red graph. That has no cycle in it. That's by the first part that we proved. T is a tree. It has no cycle. So C is not contained. So let's just say not a subgraph of T, right? This blue thing plus the red edge is in this graph, but it's not in just T. So what does that mean about this cycle C here? Like these edges that make this thing up are not all, they don't all appear in T because T doesn't have a cycle. So what do we know for sure?
Is it that T is a subgraph of C?
No, not necessarily. Not necessarily. So keep in mind, C may have very few edges compared to the whole graph. Like it might just be 3 edges. In fact, it might just be a tiny part of the blue graph.
There must be an edge in the cycle that is in T star, but not T.
Good. Yes, exactly. So there's got to be a blue edge here that's at least one, probably more, that are not a part of T. Because if all these edges are present in T, then T has this cycle, right? So there's got to be an E prime that's not in T, okay? So C is not a subgraph of T, so there exists an E prime that's in the cycle such that E prime is not in T. This E prime is just like a witness, right, for the fact that C is not contained in T. There's got to be at least one edge of it that's missing, okay? All right, so yeah, this means that so E prime never appears in T. So this means that when we were about to add E to T, that E prime was available. Okay, so what I'm talking about is the algorithm here. Let's think about the algorithm for a second here. So T runs, and eventually it adds edge E to T, right? Edge E is in T, so there was a point when we added it. And we did add it to it. Now, E prime was never added to T, and we couldn't have, so what do I want to say here? This was added. Right, okay. E prime was not added, so it meant that it was always available to be added to T. Like, I mean, at some point it was examined and not added, right? So think about it this way. So T is built up by adding an edge to it one at a time. We always add the lowest weight edge unless it creates a cycle. E prime could not have created a cycle in T at the point we were adding E, because like this is the cycle that contains both those edges. And like if I added E prime instead of adding E, I would not have got a cycle because the cycle with E prime requires E as well. So that meant that when I was adding E to my graph, alternatively, I could have added E prime. It was available. Why wouldn't I have added E prime then? Why would I choose E over E prime as far as the algorithm is concerned? How does the algorithm make a choice between one edge versus the other if they're both like permittable to add, if neither creates a cycle?
E must have or less weight or at least equal weight and chosen first.
Yes. Does that make sense? So thus, the weight of E was at most the weight of E prime. That's why I would have chosen E instead of E prime. If E had strictly more than E prime, then I would have chosen E prime at this step, okay? And that's what it means. It had to come earlier in the ordering. So not only was it less than or equal to, like if they were equal, somehow the tie was broken in favor of E. That's how we produced T here, okay? So now examine the following. T star, that's the red, right? That's the red spanning tree, which is a minimal spanning tree, this hypothetical spanning tree. Let's look at T star. Let's add to it E, which creates this cycle, right? Which we've done a moment ago, and then subtract from it E prime, right? So this is a new graph, right? This is like we've got T, so T star, let me add some more blue edges here. Like T star is here, and inside of T star is this blue part here. When I added E to it, I created a cycle, okay? But let's destroy that cycle by removing E prime. Whoops. So what can you tell me about this graph? Well, this is a spanning tree. Okay. If you don't see that immediately, it follows from the tree properties, but it has to do with minimal connected. We lost an edge and gained an edge and didn't gain a cycle, and so we actually have to remain a tree, and moreover a spanning tree, right? We still have the same number of vertices. How does the weight of this graph compare to T star? Well, we removed E prime and replaced it with E, which according to this meant that the weight didn't increase. And actually, it shouldn't decrease either, right? If it decreased, then this would be a spanning tree with smaller weight than T prime, right? So actually, this is a minimum weight spanning tree. It's a new spanning tree that's still of minimum weight, right? It can't be lower than the minimum. But what is the relationship between this spanning tree and T? But T
it has more edges in common.
Exactly, but T and T star plus E minus E prime have one more edge in common than T and T, just ordinary T star do. But that's a contradiction because remember, I chose T star specifically that had the most in common. So this is a contradiction. And what does that contradict? That contradicts this case that we were in the first place, that the two were different from each other. And so what it means is that when I choose a minimum spanning tree with the most edges in common with T, this thing happens. It's just literally T. There's no choice but that. If it's not T, I can do a refinement and get a closer one here, okay? So again, you can prove this without a contradiction by just saying perform this like swapping procedure as many times as it takes to arrive at T star equals T. The same thing would work, but there's no reason to make an inductive proof here when you do a simple contradiction, okay? So by this like edge swapping trick here, you get something closer. And so you know that T is equal to some hypothetical minimum spanning tree. In other words, T is a minimum spanning tree. That's how we prove it. We compared it to something we knew existed, even though we couldn't produce it, okay? Now we know how to produce it. Kruskal's algorithm's fantastic. It produces minimum spanning tree very, very fast. You can see it's not hard to check if adding an edge will create a cycle. It takes a little bit of work. And you know, there's only at most n choose 2 many edges to examine in the first place. Okay, so I want to try and finish a little early today. So I'm going to mention 2 other algorithms. I'm not going to prove them. The second algorithm is proved in the notes anyway, and the technique is similar to this one, so you can go ahead and read through that. But let me mention the other ones here. So there's the Yarnik Prim algorithm, just discovered by these 2 people independently, not by them jointly. And it says, okay, so again, G is a connected graph with an edge weighting. I'm not going to write that out there. So it says start with T an arbitrary vertex of G. So T is just some random vertex of G, whatever it was. And then we're going to have this iterative procedure again. Before we found the lowest weight edge that we could and added it, now I'm going to do the lowest weight edge that's incident to what I've built up so far. So add to T a smallest weight edge with exactly one end vertex in T. Okay, let's run this on our graph real quick here that we've been using, if I can remember the details. I mean, if I can remember the numbers, 1, 9, 4, 3, 2, 6, 6, I think it was. So this may end up producing the same spanning tree, but the procedure is a little bit different, right? So in Kruskal's, so okay, first of all, Kruskal says take the lowest, and then the lowest, and then the lowest, and then, oh, you can't take that lowest. You just keep trying to add the lowest to it, and then eventually build the tree. Here, we're going to start with an arbitrary vertex. Let's actually start with this vertex. It's natural to start with a vertex incident to the lowest weight edge, but you don't have to do that. You can start anywhere you want, okay? But for this first run, let's do it that way. So we start here, and we look at the lowest weight edge incident to t. Well, t is just a single vertex, so I just look at all the edges coming out from it. -1's clearly the winner, okay? Now in the second step, in this graph here, this 2 vertices and 1 red edge, I look at the lowest incident edge to it, okay? So now Kruskal's would add 2 here, but that edge 2 is not incident to this thing here. So the procedure has to do something different. Here it adds 3, right? Now again, look for the lowest weight. Oh yeah, exactly. So we're fine. How do we avoid a cycle? Kruskal said just don't add if you get a cycle. This says look for the lowest weight edge with exactly 1 endpoint incident to what we have so far. So that says this 4 edge can't be chosen because both of its endpoints are in there, which of course would create a cycle. So that's great. We avoid that. And then it says, okay, choose 1. So the 2 choices are 6, 9, or 6. So we can choose either of those. It gets a similar situation to Kruskal. It doesn't always occur at the same time. We choose 6. And then the last step is to choose 2. So this actually doesn't produce a different spanning tree than the previous. There are ways to make them choose different ones if you're careful with your edge weighting, make the graph large enough. But you can see the procedure is very simple. We didn't have to start here. This is a natural place to start. We could have started anywhere. Maybe I'll just draw it on the same one here. You know, if I started with like this vertex here instead, then it would say choose 3, and then it would choose 1, and then it would choose 6, and then it would choose 2, right? Van, do you have your hand up?
Yeah, I was wondering, like the way that these are phrased, I feel like they would work also for multigraphs.
Yeah, so that's a great question. I didn't think about that, but so for multigraphs, when you're looking for spanning trees, if you have multiple edges, you can remove the highest weight among those multiple edges, because if you're going to choose an edge between those 2 vertices, you would never choose the weight, you know, like let me draw, but like if you had this situation here and there's a 3 here and a 5 here, like there's no spanning tree imaginable. I mean, minimum spanning tree that would ever use this edge here when you have access to this edge here.
So then you iterate and then just make it a tree, basically.
Yeah. I mean, you could pre-process by just removing the higher weight multi edges if you liked. Let's see here. But even if you didn't pre-process and just ran it, you'd be fine, because if you ever added edge 3 here, edge 5 would not be added by Kruskal ever, because that creates a cycle. We never defined a cycle of length 2, but this is considered a cycle when you take, you know, 2 edges on the same 2 vertices. That makes sense to be a cycle, right? And then
a loop being a cycle of length 1 even.
Yeah, absolutely. That's a good point, Van. Yeah, also a loop you wouldn't want to add a loop to a spanning tree. It doesn't help you like gather up the vertices, and loops are generally considered cycles as well. And same thing, Yarnik Prim wouldn't add this either, because this, if you've added 3, this is an edge that has 2 end vertices so far in your graph, so you wouldn't add it. So you could pre-process or you could still run it. Both would work fine. Wouldn't be any issue. Okay. All right, and let me add one more here, which is actually the sort of the older one, the oldest of these, and in some ways the most superior. Although there are other algorithms out there today as well, but this is Borufka's algorithm. And what's nice about this one is this was like literally implemented to figure out how to build electrical networks, like electricity networks in Moravia, like in the 1930s. So it's like this is predates graph theory almost. So this one says start, and this, if you think about it in one way, if you implement it one way, it'll actually be equivalent to Yarnik Prim, but you can be a little bit more clever with this one. So start with empty graph. Okay, let's not say empty graph. Start with graph, let's say with spanning graph with no edges. Okay, so what does that mean? T is just like literally the vertices. That's what T starts with. So start with T is a spanning graph of G with no edges. So I just like start with all vertices simultaneously. I know that all vertices are going to end up in the graph that I produce. Let's just suppose they're all there to start with. Okay, and there's a reason why I've written it in this way, because of the like iterative step here. Okay, so now at each step, for every component C of T, add a minimum weight. all, let's see here. Let's add, let's see here, add a minimum weight, add, let me rewrite this. Minimum weight edges. So we actually add multiple edges here. It's up to you how you're actually able to implement things. You may end up not doing it simultaneous when you actually implement it, with exactly one end vertex in C. Okay, let me illustrate here what's going on here. Okay, so say we have G, and I've got all the vertices of G. Okay, in this first step, what are the components of this graph here? Like I've got a bunch of edges here, but I start off with T, just literally being the vertices of the graph with no edges there. What are the components of this, of T?
All the vertices.
It's like literally all the vertices. So we have a bunch of vertices here. So what Barufka says is for every component, I want to add the minimum weight edges with exactly one vertex in that C. So each of these guys, I'm going to like look for the minimum weight that's incident to this guy here and say, okay, great, add that one there. Okay, maybe I haven't written this out perfectly, but in adding this edge here with this guy here, I'm not going to add another edge out of this guy here. Okay, and then I'm going to add an edge here, an edge here, an edge here, and like, okay, and then an edge here actually is possible here. So the first step, you can actually run this in parallel. You're going to basically get n over 2 edges. Now in the second step, I've got half as many components, and I'm going to add a minimum weight edge among pairs of components here as well. Okay, yeah, I haven't actually written out Barufka's very nicely here. It makes it a little bit hard to understand, but you can add minimum weight here, minimum weight here, minimum weight here, and then each time I add these edges here, what happens?
Well, adding an edge combines 2 components, right?
Yes, exactly. So I start off with n components, and then adding those edges each time I add an edge. So if you don't try to run it in parallel and just add an edge at a time, like when I added this first edge, this took this component and this component out of the running, and now among what's left, I have to look for a new edge. If you implement it carefully, you can do this in parallel, which is like really cool. But even if you don't do it in parallel, each step here is reducing the number of components by 1. And so if it's actually done in parallel, you're halving the number of components at each step, which is usually a good sign when you're trying to run an algorithm, right? So this is going to have something to do with like log n runtime. Again, runtime of algorithms is not something I want to focus on much in this class. But if this is implemented carefully, you can get it to go very, very fast, okay? I'll stop there.